I just finished one of my exam. So do you have any quizzes or tests in class?
No, but I hope to grade them all by tonight and kind of tomorrow.
I was just wondering, there's no rush. I just thought you put it in, so I thought you maybe you handed it out.
Yeah.
Okay, cool. Thank you.
And if you pick up, were you here in class today?
No, I wasn't here.
Okay. What date? Which date do you know?
This will be.
This will be okay. Let me make sure. Yes. And
I did not. Yeah. No.
okay. So let's put that down. This is the 2012-2014 multiple choice exam. It's not homework, it's a practice.
Okay.
This is the current 20.
Those are like all the FRQs.
FRQs that we're working on right now.
I had those.
Okay.
They actually gave out last week, I think.
Okay.
Yes. All right. Thank you so much. Good one. I'll see you tomorrow.
See you tomorrow, Joe. Okay, so page 18, we're looking at number 4. Okay, so to begin here, the height of a tree at time t is given by a twice differentiable function, h, where h is measured in meters and t is measured in years. We see that as time passes, the height in meters of the tree will keep growing. Like the values of h of t are given. Part A says use the data in the table to estimate h prime of 6. So in other words, it's asking for what is the rate of growth of the tree 6 years in. So, I mean, if we had a h of t equation, then we can find the derivative, but we don't. So the best thing we can do is to find the slope and pick the two closest points, which is 5 and 7, and do change in height over the change in years. That'll give us our approximation for h prime of 6. So h of 7 minus h of 5 over 7 minus 5. So change in height divided by the change in years, and that averages out to be, or comes out to be 5/2, and that's our best approximation for what could be happening in the 6th year. 5/2 meters, growing at a rate of 5/2 meters per year. Yeah, you want to use the closest. Yeah. Now, if it was asking for h prime of 5, then you have the choice, because h prime of 5, you could say, okay, I can make an argument for 5 and 7. I can make an argument for 3 and 5. I can even make an argument for 3 and 7. But if 6 is between 5 and 7, the best option is always 5 and 7. Oh, okay, you're looking at mean value theorem, maybe. Okay. All right, so part B, explain why there must be, so this is a guarantee, they're saying this is guarantee, why there must be at least one time t between 2 and 10 such that h prime of 2 or h prime of t is equal to 2. Okay. So there is going to be a time t. Whenever we see this h prime of t is equal to 2, they're trying to get us to reference something. So the idea is h prime of 2 is basically saying slope, right? And if I'm given all these values as h of t, and I want to guarantee a slope, that's basically kind of telling us to maybe explore mean value theorem, right? Because mean value theorem allows us to connect average slope with instantaneous slope. So if I can show that there's a slope of 2 at any of these points, then I know there must be a specific slope of that value somewhere in that interval. So I'm going to start at 2 and 10 first to see, can I see a slope of 2 between the endpoints? So 15 minus 1.5 gives me 13.5 divided by 10 minus 2, which is 8. So it's close, but it's not quite there. So normally the AP exam doesn't do this, where you have to kind of go searching for order pairs to match that slope. They usually give it to you at the end. But I think in this case, maybe it's not too difficult to just look for quickly at some order pairs here and see if I can get a slope of 2 to show up. And it looks like once I'm looking at these the second and third order pairs here, 3, 2, and 5, 6. 6 minus 2 is 4, 5 minus 3 is 2, 4 over 2 is 2. So we're able to get that slope without having to do a whole lot of guessing and checking. So since we're able to locate a slope of 2 between 3 and 5, then we can guarantee that there must be at least one time t between 3 and 5 that feels more specific than 2 and 10, where there's a slope of 2, right? If there's an average slope of 2 somewhere along the curve, or between the endpoints, then somewhere along the curve, that graph has to reach that exact slope. Okay, part C. Use trapezoid sum with 4 subintervals indicated by the table to approximate the average height of the tree over the time interval from 2 to 10. So I see trapezoid sum, so I know I have to involve this area formula 1/2 width height 1 plus height 2. But at the same time, I also see this approximating average height. So I'm also thinking I got to involve 1 over b minus a integral from a to b of f of x dx. So I need to kind of merge these two together. I know that area will take care of this integral, will represent that integral notation, but I need this 1 over b minus a as a way of going through that average value theorem. So I look at each of the subintervals here, subtract all the widths, that will give me, or subtract all the x values, the t values, that will give me the widths that I'm involved in, and then all the heights, all the meters, height in meters will be representative of the height of each of my trapezoids. So here's my setup. Don't want to forget about that 1 over b minus a, which is 1 over 10 minus 2. And the integral is going to be represented as an approximation using trapezoid, area of trapezoids. So width over 2, or width times 1/2 times width, height 1 plus height 2, 1/2 times width, height 1 plus height 2. Same thing all the way through. Now, my suggestion is leave your answer in unsimplified form, because if they're already going to give you credit for this work, then there's no need to spend an additional 5 minutes trying to get it down to a number, right? So you have better use of your time elsewhere on the test rather than working on something that's already going to give you full credit. Okay, A, B, and C. Okay, so far. Okay, part D is the part that feels a bit more challenging here. So let's look at part D. Part D says the height of a tree in meters can also be modeled by the function g given by g of x, okay, where x is the diameter of the base of the tree in meters. Okay. When the tree is 50 meters tall, the diameter of the base is increasing at a rate of 0.03 meters per year. According to the model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So you see how now there's time involved within an equation, and that should give us a hint that this is going to be a related rates type of a problem. Related rates is where every variable that we're working with is going to produce a d over dt. So a g will produce a dg dt, and x will produce a dx dt. Okay. So we know for part D, we have height. Function g is equal to 100x over 1 plus x. Okay, let's gather all the information that we can. It says when the tree is 50 meters tall, so that's the height. Height is g, so we know that g at the moment in time is going to be 50. We'll gather that information. The diameter of the base of the tree, and x represents the diameter. The diameter is increasing at a rate of 0.03 meters per year. So we know that our x, dx dt is going to be positive 0.03, right? According to this model, what is the rate of change of the height of the tree? So we're looking for dg dt. When the tree is 50 meters tall. When g is, yeah, so we already have that. So g equals 50. So we have all this information involving dx dt, dg dt. So we got to build our derivative to get those variables to show up. Okay. So let's go ahead and find our derivative. G becomes dg dt. Okay, what about the right side? What do you think we have to involve here to find the derivative? Numerator, denominator, quotient rule, yeah. So f prime g minus fg prime all over g squared. And along the way, we're going to get dx dt to show up when it calls for it. F prime, 100x becomes 100, but the x is going to turn into dx dt since time is going to impact everything here. Back to f, g prime, denominator squared. Okay, so we want to start inserting information in, but there's something that feels a little strange here. I'm looking for dg dt, which is fine. I have dx dt, which is good, but I'm missing x. So is there anything that I can do to fill in for x? Because right now I'm still I don't have x available. Is there any way to solve for x before I start using this formula? So, any idea? How about this equation? Right, it's kind of like Pythagorean theorem, where when we knew that we're missing a variable, we can always go back to the original equation and try to find some relevant information that we need. So we're going to have to work back. So there's a lot of algebraic steps here. We have to insert that 50 in for g and kind of cross multiply and solve for x so that we can have enough information to insert into my derivative. Okay, cross multiply here. That's a nice easy number. That's good. So we have everything that we need now. Okay, so dx dt 1 plus 1 minus dx dt again, 0.03, all over 1 plus 1 squared. This is a mess having to clean all this up. It ends up giving us 3/4. And we know that G is in terms of meters, time is in terms of years. So we know that it's meters per year. However, this is part of a non-calculator section. So we want to just leave our answer like this. Okay. If everything is numerical, no trig, we don't have to clean all this up. As long as you're showing the grader that you know where all these numbers are coming from, it's just you're just a calculation away in the calculator to getting the right answer, they'll accept this answer. I think the tough part with D is recognizing the need for related rates and then following through with all the steps required from related rates. Okay, number 5. Okay, let f be the function defined by e to the x cosine x. Find the average rate of change. So it's not asking for average value, it's asking for average rate of change. So that's just the slope between the endpoints. Okay. Okay, so no derivative here. We just are literally just going to do change in y over change in x between those endpoints. So I'll find f of 0, I'll find f of pi, and then just subtract those y values from each other. Anything raised to 0 power is 1, cosine of 0 is 1. e to the pi will stay as e to the pi. Cosine of pi is -1, so -1 times e to the pi is negative e to the pi. Okay, so now that we have our y values, we can do change in y over the change in x. Okay, so we found those y values. Part B, find slope. What is the slope of the line tangent to the graph at x equals 3 pi over 2? So to find the slope, we first have to find the derivative, right? So derivative, what rule do we have to involve here to find the derivative? E to the x, cosine x, those are two separate terms. Got to go through product rule. Okay, f prime g plus f g prime. Sorry, did you see my work for the previous problem? I don't know if it was on freeze the whole time. You got everything here? Okay. Now that I have my derivative, I can find my slope, evaluate my derivative at 3 pi over 2. Cosine of 3 pi over 2 is 0, so that's going to wipe out this entire first term. E to the 3 pi over 2 is just going to stay there. Sine of 3 pi over 2 is -1, so negative times negative is positive. I'm just left with a positive e to the 3 pi over 2. Okay, part C. Find the absolute minimum of the value of f on the interval from 0 to 2 pi. So absolute minimum, that should remind us, that's a hint that we have to involve EVT, extreme value theorem. And with the extreme value theorem, we want to test endpoints and critical points. So endpoints, critical points, that means we know what the endpoints are. They tell that to us, 0 and 2 pi. But we also need to find critical points. which is where f prime is equal to 0. Okay, and critical points means set f prime equal to 0 and solve for x. Okay, so we have our derivative. Let's set our derivative equal to 0. We already know what the endpoints are. We'll set that off to the side, but we need to test the endpoints. Well, we need to find the critical points. So take my derivative, set equal to 0. I can factor an e to the x out. Okay, so I have two parts. Factored form, I can set the e to the x equal to 0. I can set the cosine minus sine equal to 0 and see if I can find any critical points from those from these variables. Okay, e to the x equals 0. This is never going to happen. E is always going to hover above 0. If I try to take natural log of both sides, you're also going to see that we're going to run into an issue because natural log cannot exist at 0. Natural log of 0 is undefined. So we know there's nothing here. We can move on to the other one. Now, cosine minus sine equals 0. This feels a little bit harder. It's like, how do I solve one in terms of the other? Well, what if I set them equal to each other? Cosine of x is equal to sine of x. Okay. Doesn't feel like we're making much progress, but what if we divide both sides by sine? Or better yet, what if we divide both sides by cosine? What's another way of calling sine over cosine? Tangent, right? So tangent is equal to 1, and all of a sudden, this feels a lot easier to manage because we know where tangent is equal to 1. Tangent is equal to 1 at variations of power 4. First and fourth quadrant. Sorry, first and third quadrant. Okay, so there we have it. We have our critical points that we're testing. We have our endpoints that we have to involve as well. So now we're going to insert them all into the original function and then see which one produces the absolute minimum value. Okay, we're trying to find the absolute minimum. So it's easy to spot because the absolute minimum here, there's only one negative value, and that's going to be lower than the positive numbers. Okay, good so far? Okay, part D. Let g be a differentiable function such that g of pi of 2 equals 0. The graph of g prime, the derivative of g is shown. This is g prime. Find the value of the limit as x approaches pi over 2 of f over g. Justify your answer. So this, anytime I see a complex limit problem, I'm instantly going to start thinking maybe this is L'Hopital's rule, but we can't jump into that conclusion until we actually get confirmation. So what's the first thing we're going to do? If we see a limit problem. Yeah, just plug it in, right? Let's go through substitution and just see what we're dealing with here. Oh, and also, if you're dealing with limits, go ahead and always use arrows, right? They're picky about those. So just, for response, don't even mess with equal signs, especially with things that involve limits. So I get f of pi over 2 over g of f of pi over 2. If I plug pi over 2 in for x, e to the pi over 2 times cosine pi over 2. Cosine pi over 2 is 0. Anything times 0 is 0. G of pi over 2. Well, they tell us g of pi over 2 is 0, so I have that. Okay, so we can apply L'Hopital's. So L'Hopital says find the derivative of the numerator and then separately do the derivative of the denominator. This is not quotient rule here. We're just going to find each derivative separately because our purpose is not to find full derivative. Our purpose is to use the derivative to achieve our goal. Okay, so let's go through our next step. Once we have 0 over 0, we found the derivative of the numerator and denominator. We're going to reevaluate. F prime of pi over 2. So f prime is, oh yeah, it's over here. So we'll just insert pi over 2 in for x. G prime of pi over 2. So we have G prime here. So G prime of pi over 2 is going to be at 2, right? So this is the G prime graph. So I can just pick it off my graph here, 2. Do some cleanup here. Cosine of pi over 2 is 0, so that goes away. I'm just left with negative e to the pi over 2 times sine of pi over 2. Sine of pi over 2 is 1. So I'm just left with negative e to the power of 2 over 2. That's a real number, so we can stop. We found our limit. Good. All right, number 6. Consider the differential equation. A slope field is given. Sketch the solution curve that passes through 0, 2, and that passes through 1, 0. So it's 2 separate graphs. We just kind of follow the pattern of the graph. So if I'm going through 2, it's going to go right through. So the curved segments is going to kind of, it's like a stream, is going to kind of help me decide how to move through. So I'm going to just kind of follow this pattern here. Part D, let f of x be the particular solution. We have our order pair, we want to find the slope. We'll do point slope form, and then we can do linear approximation. Okay, so I'm going to put this up here. I'm going to save that bottom space for part C. Okay, my point is 1, 0. My slope comes from my dy dx, right? That's my derivative. Derivative is my slope formula. Okay, negative 2 squared is 4. 4 over 3 is 4/3. That's our slope. Point slope form. Solve for y. Okay, so once you have your linear equation, all you're going to do now is insert that decimal to get that linear approximation. Now, even though negative 0.4 is the answer, we're going to encourage students to just stop here, right? This is good enough. There's no need to go any further and risk making a mistake if you're already sitting at the right answer. Okay, so linear approximation for part B. Part C is where we're going to work towards solving this differential equation. So here's part C. I'm going to write this as a fraction so I can see the numerator and denominator parts clearly. Just pushing that 3 to the denominator to make it easier for me to cross multiply. Okay. First order of business, let's try to get the dy dx's in their right places. Then we can worry about getting the x's and y's in the right places. Okay, I see a few things out of place here. My dy dx's are locked in, that's good. But I would like my y's together, so I'm going to divide this y minus 2 over, make it go to the denominator. And this 3, let's just go ahead and move it back, right? There's no need to have that 3 on the left side. Eventually, it's going to come to the left anyway, so I'm going to just, we're just going to go with the x anyways. So we'll do a double division here. I'm going to divide the y minus 2 over to the left, and I'll divide the 3 over to the right. Good so far? Okay, all right. Set up our integral here. Left side is u substitution, right side is power rule. But even with u substitution, I like to get that to be brought up to the top so I don't have to worry about moving it up later. Okay, use substitution on the left. Power rule. So we took care of our calculus, the plus c shows up, and everything else after is just algebraic. We're going to bring the y back, solve for c, and solve for y. So I figured, why don't we just go ahead and solve for c here before we got to deal with flipping everything around and just. But ultimately, you can solve for c at any point in time. I'm just kind of arbitrarily deciding that this is a easier spot for me to do this in. So I'm just going to go ahead and plug in and find my c value. Order pair 1, 0, 1 in for x, 0 in for y. Let's see where that takes me for my c value. One half is equal to 1/6 plus c. Subtract 1/6 from both sides. Same thing as 3/6 minus 1/6, which is 2/6, which is 1/3. So my c is 1/3. Okay, we go back to where we made that substitution for our order pairs. And try to solve for y. Feels weird having to flip this y minus 2, but if I want to flip it, I would like this all to be one fraction. So at this point, you pretty much earned all the points. You may have to solve for y, but algebraically, it's going to feel like a lot. Sometimes maybe it's not worth the trouble to spend 5 minutes on this when you can figure out other stuff. You know what I'm saying? So sometimes it may not even be worth going through all this trouble just to try to get this one final point, but we can go through and get some practice in. Common denominator is 6. X squared over 6 plus 2 over 6. If I flip this, I can flip this as well, now that I have a fraction equaling a fraction. And then I'm also going to multiply the negative over to the right side as I flip. Just going to try to get that y as clean as I can. It's the same thing, right? 2x squared plus 1
not sure why my key is showing a different answer. Yeah, I think I'm right here. I think my key may be wrong. Okay, so I'm going to add 2 to both sides. It's always good if we can double check with the order pair and see if it'll work. It should work. If I plug 1 in for x, get 1 plus 2 is 3. Negative 6 over 3 is negative 2. Negative 2 plus 2 is 0. Good way to double check we're on the right track. So, okay, any questions? Okay. All right. Tomorrow I'll go over the 2017 FRQs, okay? Okay, sounds good. That'll be good. Yeah.